Hello students, welcome to Sri Jayendra's Ring Zone classes. I am your friend and mentor for coming classes with respect to physics. This is lecture number 8 of unit moving charges and magnetism. So this is basically the second part of Ampere's circuital law. As we have discussed in the previous class that according to the Ampere's circuital law, we can have it's a line integral of B dot dl is equals to mu naught times of I enclosed. We are talking about the I enclosed. That means, let's say this is the current carrying conductor and this is the circular loop and this current is going. Then I understood that this is I1 and this is I2. So when I go for the I enclosed, I will write only the I1 and not the I2. Yes, one thing. But when we have been asked, when I have been asked for the magnetic field contribution, then I will go with the I1 as well as with I2. Yes, as I2 is not enclosed by the Amperian loop, but it is the part of the magnetic field contribution in this region. Yes, so this was the Amperian circuital law, and we were discussing the applications of the Ampere circuital law. We have already discussed the applications of the straight wire. It means infinite straight conducting wire for the cylindrical conductors, solid as well as hollow. I hope this is clear. Now let's work for the next application, and this is magnetic field due to solenoid. So before I go with the solenoid, before I go for the magnetic field due to solenoid, do you understand what solenoid is? We can say that let's suppose this is a straight wire, and this straight wire is going to be converted into coil something like this. I hope this is clear. This is a diagram I have shown. Yes, it is just the 3D version of this diagram. I hope this is clear. So basically a solenoid is just a number of circular coils. It covers a number of circular coils. Yes, and ideally, in the ideal situation, we consider that N is the total number of turns of solenoid, and we represent small n, it's a number of turns per unit length. Yes, so this is n is the number of turns per unit length. Small n is the number of turns per unit length. This is n. Yes, so and let's assume that I amount of current has been flowing, and then we used to find out the magnetic field due to solenoid. So before we switch to that, do you understand what solenoid is? Yes. Now let's look at the magnetic field due to solenoid according to the Ampere circuital law. So what I have done is that I have divided this. That means I can use that I have cut it from this segment like this, something like this. I hope you understand it. Yes, I have divided it like this, and the front view of that sections would be visible like this, that current has been entering through this region and current has been leaving through upward region. So from this current is going down, from this current is going up, and what I am supposed to do is I have taken 1 ampere loop that will represent A, B, C, D. So it's A to B, B to C, C to D, and D to A, and the length of this loop is A. I hope this is clear. Now what my basics is, the basics says that according to the Ampere circuital law, line integral of B dot dl should be is equals to mu naught times of I enclosed. Yes, So line integral of B dot dl is equals to mu naught times of I enclosed. When I say it's a line integral of B dl, what I need to do is I need to go for the line integral of A to B, line integral of B to C, line integral of C to D, and line integral of D to L. That should be is equals to what? Now let's have a look. That first, let's understood it one by one. So for A to B, let's suppose DL is in this direction, DL is in this direction, and magnetic field is in this direction. So as this is 90-degree, and when it is a 90-degree, it's a B dl cos 90. So this will form a 0. This is the case of A to B. Now let's understood the case of C to D. The direction of dl, it is in this direction. Direction of magnetic field, it is in this direction. So this is again 90-degree, and as it is a 90-degree, it's a B dl cos 90, and that would be a 0. I hope these things are clear. Is it clear? Is it clear? Great. Now let's understand the case of the BDA. As you can see that this section is just the outside the loop where current is flowing. So in this case I enclosed would be a 0, and as I enclosed would be a 0, it's a line integral of B dot dl, that would be equals to 0. So what I understand is that AB is 0. Why? Because of 90-degree. The CD is 0. Why? Again because of 90-degree. This is 0 because of I enclosed is 0. Now only the term that left, it's a BC. It's a line integral of B dl from B to C, and B to C, as this is the length A, this must be the length A, and when it is a length A, it should be equals to B into A. This is line integral of B dot dl, that should be is equals to B into A. I hope this is clear. Is it clear? Is it? Great. So let's just write it down. It's a line integral of B dot dl should be is equals to mu naught times of I enclosed. The line integral of B dot dl having a value of B into A. Now I need to write down the I enclosed. How should I write this? It's a number of turns per unit length, N by L, that we have already defined, multiplied by A multiplied by I, and that would be equals to B into A. So if I relate it correctly, it's a mu naught times of I enclosed. So B dot dl, it's a B into A, should be is equals to mu naught times multiplied by I enclosed. I enclosed could be written as N into A into I. I hope this is clear. Yes. So this is equals to this A, and this A has gone, and I am left with the mu naught N and I. So this B should be is equals to mu naught times of N into I, where N is the number of turns per unit length. It's a number of turns per unit length. Yes. Is it clear? Is it clear? Is it? Now is it clear up till now? This is just the magnitude. What about the direction? What about the direction? How could you identify the direction of the magnetic field? How could you? So what you need to do is to find out the direction. You need to use your right hand, and when you use your right hand, let me see you that this is the outside. Yes, we have seen, we are just trying to show you the cross-sectional view, or upper view, top view we can say, of the solenoid. So from here current is moving downward, and from here current is moving upward. So use your right hand, and just curl your fingers of right hand. in the direction of current, the direction of current, and thumb will represent thumb will represent direction of magnetic field. Yes, so curl your fingers of right hand in the direction of current, and your thumb will represents the direction of magnetic field. So in this case if you use your right hand, that such that current on from the upward side, current from the upward side is moving in the outside the plane, the magnetic field thumb is representing in this direction. Yes, now let's suppose the situation is like this: from the upper side current is moving downward, and from the bottom side current is moving outside the plane. So if you again use your right hand, if you use your right hand, then you will find that from if you curl your fingers such as that current is moving inside the plane of the paper from the top of the side, then the thumb will represent in the negative x direction. So this is the b or direction of magnetic field. I hope this is clear. Is it clear? Yes, it is the same thing that we have used for the coils. Basically it is a combination of so many coils, and they have been arranged such as their magnetic field, or I could say a magnetic field due to each one an individual one, is going to add it up. That's it. This is nothing new for us. Yes, this is just the new form for us. Probably it's a solenoid form. I hope this is clear. Is it clear? Is it great? Now let's understood mu naught Ni very carefully. Let's suppose and consider that this is my solenoid. From here it is the current that is moving inside the plane, and from here current is moving outside the plane. So this is the axis of cylinder, this is the axis of solenoid, I should say it. This is the point A, this is the point C, this is the point D, this is the point E, this is the point let's say F. So what you need to do is that I need to find out magnetic field. I need to find out magnetic field at each of the location. At each of the location, and let's suppose this is just the ending of the solenoids, and these 2 points are there, A B C D E F. It's a G and it's a H, something like this. So what I understand is that location A, C and D are within the solenoid. So B at A, B at C, B at D are the B inside, and that could be represented as mu naught into Ni. Yes, it is the same irrespective of distance from the axis. Irrespective of distance from the axis, it is the same. What it would be? It would be a mu naught Ni, undoubtedly, without having a second thought. I hope this is clear. Now for point E and D, for point E and F, sorry, they are outside the solenoid. They are outside the solenoid. So for them, B at E and B at D should be equals to 0. B at E, magnetic field at E, and magnetic field at D will be the 0. I hope this is clear. Now this points H and G, this is very important. H and G are at the endpoints. and magnetic field BH equals to BG. It's a half of the, it's a half of the magnetic field which is lying inside. So please do remember this thing. Yes, even this can be proved, but that is not going to, that has not been asked ever. They only use it for the applications point of view. Yes, so magnetic field outside, it is always zero, so this will contribute a zero magnetic field. Magnetic field at A, C or D, irrespective of distance, it's a mu naught into Ni. And magnetic field at location H and at location G, at location H and at location G, it is just the mu naught into Ni by 2. I hope these things are clear. Is it clear? Is it any doubts on this? Anything? Is there anything? No? Great. So ready for the next question? Let's have a look. That a solenoid is having 5000 turns in a length of 5 meter. If current flowing through solenoid, is 1 ampere, find out first magnetic field inside the solenoid, second magnetic field outside the solenoid, and third magnetic field on the endpoints of solenoid. So go through the data carefully and let me know how should we go for it, how should we proceed, how should we do this. What does it says? It says a solenoid is there, it is having 5000 turns in a length of 5 meter, and if current flowing through solenoid is 1 ampere, then what you need to do, you need to find out a magnetic field inside the solenoid, magnetic field outside the solenoid, and magnetic field on the endpoints of the solenoid. So let's just begin what we are given and what we need to find out. We have been given capital N. Please do not make mistake. It says it is having 5000 turns. So this is capital N, total number of turns 5000 in a length of 5 meter. So better to use N is equals to N by L, which should be is equals to 5000 divided by 5, which should be 1000 turns. It's 1000 turns per meter. Yes. Now what else is given? They given that I is the 1 ampere. Magnetic field inside, it's a B inside should be is equals to mu naught times of Ni. This mu naught can be written as 4 pi into 10 to the power minus 7. N is the 1000, that is 10 to the power 3. Current is 1 ampere, it's a 4 pi into 10 to the power minus of 4 Tesla. I hope this is clear. This is B inside. Yes. Now what about the B outside? The B outside would be a 0, as we understood that outside magnetic field is 0 because it's a I enclosed would be a 0. Yes, no current is flowing through that ever. And B on the ends points, it's a magnetic field on the end points. That would be is equals to B inside divided by 2. So this is equals to 4 pi into 10 to the power minus of 4 divided by 2. What should be 2 pi into 10 to the power minus of 4 Tesla? This is on the endpoints. I hope this is clear. What was your answer? Was it same? Was it? Are you sure? Great. So let's learn a magnetic field due to finite length solenoid. In most of the case, or I should say in the 90% of cases, we used to deal with the solenoid having infinite length, and we have did it the same thing. That means we calculate the magnetic field due to solenoid having infinite length, and that magnetic field was B would be is equals to mu naught into Ni. I hope this is clear. Now we are going to discuss a magnetic field due to finite length solenoid. We are going to discuss a magnetic field due to finite length solenoid. When we are going to discuss a magnetic field due to finite length, we are going to discuss a magnetic field due to finite length. We just remember the relations. Yes, this is the magnetic field, and this is first and this is second end. When these two are the angles, then we can have that this is the length L, number of turns capital N. So magnetic field at point P at their center is, it's a mu naught Ni by 2 into bracket cos theta 1 minus cos theta 2. It's a mu naught Ni by 2 into bracket cos theta 1 minus cos theta 2. Please do remember that you need to consider angle theta 1 and theta 2. Both should be measured in same sense from the axis of the solenoid. Two end vectors. Yes, what you need to do is you are going to, from the point P, you are going to make two lines. This is the first line, this is the second lines on the endpoints, of the solenoid, and you are going to measure the value. You are going to measure the value of both the things. You are going to measure the value of the both the things such that it will end it. I hope this is clear. Yes, on the endpoints. This is the same thing that we used to have with the Biot-Savart law. I hope this is clear. So have you noted it? From this you can verify all the relations that we have used up till now. Yes, you can verify all the relations up till now, and that will be absolutely correct. I hope this is clear. Is it clear? Is it any doubts, any issue, anything? No? Great. So let's have one of the question over this. It says that find out magnetic field at axial point P at here of the solenoid as shown in the figure, and where you need to take a turn density, that is the number of turns per unit length, as N, and current through it is I. Yes, so this is 30, this is 60, but what I need this angle. So if this is 60, that should be a 120 degree. So now magnetic field at P could be written as mu naught Ni divided by 2 multiplied by cos theta 1 minus of cos theta 2. So that should be is equals to mu naught into N into I divided by 2 into cos theta 1. It's a cos of 30 degree minus cos of 120 degree. So that should be mu naught N I divided by 2 into cos 30. What is it? It's a root 3 by 2, and cos 120 degree, it's a minus of half. So that should be mu naught Ni by 2 into bracket, this minus would be the plus. So this is equals to root 3 plus 1 divided by 2. I hope this is clear. This is magnetic field at point P. Is it clear? Done it? Done? It's a magnetic field at point P, which should be is equals to mu naught Ni by 2 into bracket root 3 plus 1 by 2. Is it clear? Is that clear? Are you sure? Any issues? Any doubts on this? Anything? No? Great. So let's have certain questions over this. What does it say? Look at this. Do it quickly. There is 10 units of charge at the center of a circle of radius 10 meter. The work done, the work done in moving 1 unit of charge around the circle once. Yes, you required a work done, but you must understand that work done around the closed path is always zero. That means you are going to do the same thing. That there is 10 units of charge at the center of circle of radius. This is the radius 10 meter, and here a plus 10 coulomb of charge is given there. What you need to do, you need to move, you need to rotate this charge once around the circle. So in this case, work done around the closed path is always zero, and the answer would be the zero. I hope this is clear. Is it clear? Yes, yes. Let's have a look to the next question. It says that a horizontal overhead power lines of infinite length carries a current of 50 ampere. This is I should be is equals to 50 ampere from waste to its. It's a news, NEWS. From the waste to its, that current is moving in this direction. The magnetic field induction at a distance of 1.5 meter below the line is, yes, disregard. That means you do not need to consider it. This is the I. And what do you want? You want a magnetic field at this point. It is at 1.5 meter. So let's just put up the value and get the answer. We know the magnetic field is equals to mu naught I by 2 pi r. So this B should be is equals to mu naught into I divided by 2 pi multiplied by distance, which is r. So this is 4 pi into 10 to the power minus of 7 multiplied by I, that is of 50 ampere, divided by 2 pi multiplied by distance. It's a 1.5 meter. So this 2 pi, this is 4 pi, this is 2. It's a 52 is a 100. So this is 10 to the power 2 into 10 to the power minus of 7 divided by, this is 1.5, this is 3 into 2. This is the magnetic field. I hope this is clear. So this is 10 to the power 2, this is 10 to the power minus of 7. So magnetic field would be is equals to 2 into 10 to the power 2 into 10 to the power minus of 7 divided by 3, which should be it's a 2 by 3, which should be approximately 0.67 multiplied by 10 to the power minus of 5 Tesla. This would be the answer. This would be the correct answer. Is it clear? Is it? Are you sure? So can you do this? Very, very easy. Yes, once you remember the formula, or either once you remember the concept, this can be done easily. I hope this is clear. Is it clear? Is it? Great. Let's work for next question. It says that a current of 1 by 4 pi ampere is flowing through a long straight conductor. Okay, so current is given, which is equals to 1 by 4 pi ampere. The line integral of magnetic induction around a closed path. The line integral of magnetic induction around a closed path enclosing the current carrying conductor. So current is given, it's a 1 by 4 pi ampere. I is given, it's a 1 by 4 pi ampere, and you need to find out the line integral of magnetic induction. This is line integral of B dot dl is equals to mu naught times of I enclosed. So either you calculate this or you calculate this. What I find, it's easier to find out the I enclosed because I is given. So let's have it. It's a mu naught times of I enclosed. Mu naught 4 pi into 10 to the power minus 7. I enclosed. It's a 1 by 4 pi. This 2 has gone. And the line integral of B dot dl. It's a line integral of B dot dl. It's a 10 to the power minus 7 Weber per meter. That's it. You did it. Great job. I hope this is clear. Is it clear? Is it? Is it clear? Okay, great. Let's work for the next question, last question of this class. But it is a very good concept. Even you need to remember this formula also. So let's have a look. What does it say? It says that a large metal sheet carries an electric current along its surface. Okay. Current per unit length, it's an I by L is lambda. That is what they have given. You need to find out a magnetic field near the metal sheet. You need to find out the magnetic field induction near the metal sheet. So how should you do this? How could I? Look at this. A diagram has shown, and the diagram is representing that current is flowing and it is just from moving from the outside the sheet. Yes. So what I need to do is, let's understood that let's suppose this is length L, and as it is a metal sheet, yes, even this should be, even this would be the length L. Yes, so I'm going to do the same thing. It's a line integral of B dot dl should be is equals to mu naught times of I enclosed. So it's a length of L, it's a length of L, so this is 2L. So it's a B into 2L or 2BL. That should be is equals to mu naught times of I enclosed. Now I enclosed can be written as lambda into L. So this is mu naught times of lambda into L. So let's just compare this. This L has gone, and the B should be is equals to lambda times of mu naught by 2. Yes, if lambda is constant, and generally in most of the cases it is constant, then you can understood that this is the magnetic field, which is uniform magnetic field, because when you have seen it's a mu naught I by 2 pi r and something like this, that means they were the non-uniform magnetic field. This is the uniform magnetic field. It's a source of uniform magnetic field. I hope you understand this. Is that clear? Great. So please do remember this. Please do remember this. This is very useful result that we can use in many of the applications. I hope this is clear. Is it? Is it clear? Great. So let's just wind it up this session over here. Yes, this was all about Ampere circuital law. We have discussed this into two parts, part 1 and part 2. We have completed all the applications, we have done the numericals. So Ampere circuital law is open for all to make and to solve numericals based on Ampere circuital law. So up till now we have begin with the introduction to magnetic field, then the motion of a charged particle when it has been placed or when it has been thrown in uniform magnetic field. Then we have switched to the Biot-Savart's law, then its applications, and now it's a Ampere circuital law. So we have completed approximately 60% of unit. So why I am telling you this? Because you must understand that you need to attempt questions based on all of this. Yes, please do at least 30 to 40 numericals of physics each day, every day, without failure. Yes, this will help us, this will save our times in the examination, and this will increase our accuracy during the examinations. You will find that while doing this you will reduce your errors. I hope this is clear. So please do it, please do it. Thank you, have a good day, take care, bye bye.